Hello, today we're looking at the derivative of the exponential function, or e to the x. And as usual, we are dealing with formulas on page 25 of our log tables, or our formula tables. Now, e to the x is a very unusual function, particularly when it comes to differentiation. Because if we have a function y is equal to e to the x, and we get its derivative, that is also e to the x. It does not change. This is unusual. It is actually one of the ways of defining the exponential function. We won't really get into that, but it is actually one of the fundamental properties of the exponential function is that it is its own derivative. Now, what we're going to do is just look at how to deal with that in practice. We have y is equal to e to the 3x squared. Now, this isn't quite e to the x. So what do we do in this type of situation? We use the chain rule. And in this case, using the implicit chain rule is perfectly fine. So all we're going to do is differentiate our exponential as though it were just e to the x, and then go into the function, in this case, go up into the power, and get the derivative of that, and multiply our two results together. So we are just going to use the implicit chain rule. So dy dx is just going to be the derivative of an exponential is just itself. And then we are doing the chain rule, so we're going to multiply by the derivative of what's inside our exponential function. So we have 3x squared is inside our power, so it's just going to be 6x. The power of 1 if you like. And a little bit of tidying up that we can do there. And that's all we need. That's as much tidying as we can do. And that's all there is to doing our derivative of our exponential function. It's not going to get any more complicated. Because it's not terribly mathematically complicated, it can be put into more complicated settings, however. So that's where our exponentials can be more challenging, where we have to deal with them in combination with more complicated situations. So if we look here, we have y is equal to the square root of this business. We want to get dy dx. So we're definitely going to need the chain rule here. So first rule, before we do any differentiation, is going to be turn everything into power notation if we can. Or if relevant, I should say. And now we're going to get dy dx, and again use implicit differentiation in the implicit chain rule in this case, because otherwise you would end up having to do two substitutions in the middle of one question, and it would get very cumbersome, and chances of making a mistake go up. So in this case, with the e to the x, it's best to use implicit chain rule. So differentiate the bracket. We multiply by the power. 4x squared minus 1. And subtract 1 away from the power, and we end up with minus a half. Then we step inside the bracket and differentiate what's inside. Well, the constant just goes to 0, and the exponential is just itself. And then we step one more time inside. The chain rule now has 3 steps in it, and we're going to differentiate what's inside the power of the exponential, and we end up with 8x. The power of 1 if you like. This is just algebra tidying up now. We have minus to the power of a half. Well, power of a half would mean square root, and minus means it goes underneath the line. So our next line is going to be, this stuff stays on top because it has positive powers. All over 2 multiplied by square root of e to the 4x squared minus 1. A reminder, this means 2 multiplied by a square root. This is not a 2 sitting up inside the tick here, so it just means the number 2 multiplied by a square root. Now I see I have a common factor of 2 top and bottom, so I can divide that out. And my final answer is e to the 4x squared minus 1. And that is as far as I need to go. Now, again, as we keep reinforcing as we go through this, this is a function that is valid for different values of x, so we could graph this function, and then our derivative, this mess here, would give us the slope of that function for different values of x. So it would give us the slope of the tangent to the curve of this function, as we put in different values of x. So that is what we need for derivatives of the exponent.